Picture the moment a civilization finally decides to speak. Not to a neighbor, not to a nation, but outward, into the dark, toward a star so distant that its light left home before your grandparents were born. The message is simple, a greeting, a string of numbers describing who we are and where we live. It leaves Earth traveling at the speed of light, confident, clean, and utterly certain of its own shape. And then it meets the space between the stars, and everything about that confidence begins to fall apart. For most of the 20th century, scientists imagined interstellar space as close to nothing at all, a vacuum, essentially empty, a silent corridor through which a radio signal could travel forever without losing its shape, weakening only because of the simple geometry of distance. That picture was comforting. It suggested that if intelligent life existed somewhere out there, all we had to do was listen carefully enough, or shout loudly enough, and eventually a conversation would begin. But comforting pictures are not always accurate ones, and this particular picture has been unraveling for decades. The interstellar medium, the material that fills the space between star systems, is not empty. It is a thin, restless plasma made of ionized hydrogen, helium, dust, and stray magnetic fields, stretched across light years in slow, drifting currents. Its density is almost unimaginably low, often less than 1 particle per cubic centimeter in the emptiest regions. And yet, across trillions of kilometers, even that faint haze becomes an active, physical obstacle. A radio wave does not pass through this plasma the way light passes through a clean pane of glass. It interacts with every charged particle it encounters, and over enormous distances, those countless tiny interactions accumulate into something that can genuinely distort a signal. This is where the idea of a cosmic fog becomes useful, not as poetry, but as physics. When astronomers study pulsars, the rapidly spinning remnants of dead stars that emit precise clock-like pulses of radiation, they do not see a perfectly clean signal arriving at Earth. They see a signal that has been smeared in time, spread out across a range of arrival moments depending on the frequency of the radiation. Lower frequency waves are slowed more than higher frequency waves as they pass through the ionized plasma, an effect called dispersion. Astronomers actually use this dispersion to measure the density of material lying between us and a given pulsar, essentially treating the delay itself as a kind of ruler. If a natural, powerful pulsar signal can be measured and delayed this precisely across galactic distances, then any artificial signal, however well engineered, is subject to the exact same physics. Dispersion is only the beginning of the story. As a wave threads its way through a turbulent, unevenly distributed plasma, it also experiences scattering, meaning that different parts of the wavefront take marginally different paths, refracted by patches of higher or lower density along the way. Instead of a razor-sharp signal arriving as a single, coherent front, the wave arrives smeared across space and time, its once clean structure replaced by a blurred and rippling pattern. Radio astronomers call this scintillation, borrowing the same word used to describe the twinkling of visible stars, because it is caused by essentially the same underlying phenomenon, just applied to radio frequencies instead of visible light. A star twinkles because Earth's atmosphere is a turbulent, unevenly dense medium that bends starlight unpredictably as it passes through. The interstellar medium does something remarkably similar to radio signals crossing between star systems, just on a scale that dwarfs any planetary atmosphere. Now stretch that effect across the kind of distance an interstellar message would actually need to travel. Even the nearest star system beyond our own, Alpha Centauri, sits roughly 4 1/3 light-years away. A signal aimed there does not cross a short, clean gap. It crosses an enormous volume of turbulent, magnetized plasma, threading through clouds of varying density, drifting magnetic fields, and regions disturbed by the winds of every star along the way. The farther the signal must travel, the more scattering it accumulates, and the more its original, precise structure degrades into something closer to noise. This raises an uncomfortable possibility. What if some of the silence astronomers have recorded during more than 60 years of searching for extraterrestrial signals is not evidence that no one is transmitting, but evidence that transmissions are arriving in a form we are not yet equipped to recognize? Early searches for extraterrestrial intelligence largely assumed we were listening for something close to a pure, narrowband tone, a signal engineered to stand out clearly against background noise, the interstellar equivalent of a lighthouse beam. That assumption made sense as a starting point, because a narrow, powerful, well-defined frequency is the most energy-efficient way to broadcast across vast distances. But it also assumes that the signal survives its journey mostly intact. And the physics of the interstellar medium suggests that assumption deserves to be questioned. Consider the famous WOW signal, detected in 1977 by a radio telescope in Ohio, a burst of radio energy so distinctive that the astronomer reviewing the printout circled the data and wrote the word WOW in the margin. Decades of analysis have failed to produce a fully satisfying explanation, natural or artificial, for what that signal actually was. Some researchers have proposed it may have originated from a passing comet releasing a cloud of hydrogen gas, a natural phenomenon that could momentarily mimic an artificial signature. Others consider the case unresolved. What the WOW signal illustrates, regardless of its ultimate origin, is how difficult it is to catch a transient, distorted, one-time event and reconstruct its true source with confidence. If an extraterrestrial civilization is transmitting, and that transmission has been stretched, scattered, and weakened by thousands of light-years of turbulent plasma, it may not look anything like the clean signal early search efforts were built to detect. More recent generations of infrared and radio observatories have begun mapping the interstellar medium with far greater precision than was possible even 20 years ago, tracing the density and turbulence of gas clouds across large portions of the galaxy. This mapping work is slow and incremental, built from years of accumulated observations rather than any single dramatic breakthrough. But it is steadily replacing the old, simplified picture of empty space with a far more detailed and far more turbulent one. Certain regions of the galaxy, particularly near sites of recent star formation or the remnants of past supernova, contain plasma dense and disturbed enough to meaningfully scatter high-frequency signals over even moderate distances. Other regions are comparatively calm. The result is a galaxy that is not uniformly foggy, but patchily foggy, with clear channels running alongside turbulent ones, much like weather systems on Earth vary from a calm coastal morning to a churning mid-ocean storm. This patchiness matters enormously for anyone attempting to send or receive a message across interstellar distances. A signal aimed through a calm channel might arrive relatively intact. The same signal aimed a few degrees differently through a denser, more turbulent patch of plasma might arrive so degraded that its original structure becomes nearly impossible to reconstruct. If an alien civilization exists on the far side of one of these turbulent regions, our clearest, most carefully engineered signal might reach them as little more than a faint, smeared whisper, assuming it reaches them in any recognizable form at all. And this is before accounting for the single most disruptive natural phenomenon capable of actively scrambling a signal already struggling against a passive, turbulent medium. Stars are not quiet. They do not simply sit and burn at a constant, gentle rate, patiently warming their planets for billions of years. They erupt, they flare. They periodically hurl enormous quantities of charged particles and magnetic energy directly into the surrounding space. And those eruptions do not just heat a planet's upper atmosphere or trigger auroras. They actively reshape the plasma environment through which any interstellar signal must travel, turning an already turbulent fog into something closer to an active storm. To understand why a solar storm matters so much to interstellar communication, it helps to understand what actually happens on the surface of a star during one of these events. Stars, like our Sun, generate their energy through nuclear fusion deep in their cores. But the drama that concerns us here happens much closer to the surface, in the churning, magnetically tangled outer layers called the corona. The Sun's magnetic field is not smooth or uniform. It twists, stretches, and knots itself into complex loops and arcs as different regions of the star rotate at slightly different rates and convection. Currents drag magnetic field lines into increasingly tangled configurations. Eventually, some of these tangles become unstable, and the magnetic field snaps and reconnects in a violent release of energy called a solar flare. A flare alone can brighten a small region of the Sun dramatically for minutes to hours, releasing radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. But flares are often accompanied by something even more consequential for our story, a coronal mass ejection, in which the Sun does not just release energy, but physically hurls a massive bubble of magnetized plasma outward into space. A single coronal mass ejection can carry a mass measured in billions of tons, moving outward at speeds that can exceed 1,000 kilometers per second. When that bubble of charged particles slams into a planet's magnetosphere, it compresses and disturbs the surrounding space environment, an event we experience on Earth as a geomagnetic storm, visible in dramatic auroras and, in severe cases, disruptions to power grids and satellite communications. Now scale that picture up to the interstellar level. A coronal mass ejection does not simply vanish once it passes the orbit of the outermost planet. It continues to expand outward, gradually thinning as it spreads across an ever larger volume of space, eventually merging into the broader flow of the solar wind. The constant outward stream of charged particles that every star emits. Over time, the combined effect of a star's steady wind and its more violent, episodic ejections carves out a vast bubble of disturbed plasma extending far beyond the star's planetary system. A region heliophysicists studying our own solar system call the heliosphere. Every star capable of hosting a signal-transmitting civilization is, by the very nature of stellar physics, surrounded by its own version of this turbulent bubble. And any message leaving that star system must first pass through it. This is the sense in which a solar storm functions as what the earlier framing calls a cosmic jammer, though the more precise description involves the physics of ionization and wave propagation rather than any deliberate interference. When a coronal mass ejection or an intense flare increases the density and disturbs the structure of the plasma along a signal's outgoing path, it does not chemically ionize the photons carrying the message. Since photons themselves have no charge and cannot be ionized in that sense, what actually happens is more subtle and, in its own way, more interesting. The charged particles unleashed by the storm interact with the electromagnetic wave as it passes through, altering the effective refractive index of the plasma it travels through. This bends and scatters the wave more severely than the calmer, undisturbed interstellar medium would, compounding the dispersion and scintillation effects already discussed. A signal that might have arrived only mildly smeared under quiet solar conditions can arrive dramatically more degraded if it happens to depart or arrive. During a period of heightened stellar activity, this introduces the phenomenon the outline describes as multipath scattering, and it deserves careful unpacking because it is one of the more genuinely strange consequences of transmitting information through a turbulent medium. In an idealized vacuum, a radio wave travels from its source to its destination along a single, well-defined path, arriving as one coherent pulse. In a turbulent, ionized medium, the wave does not have the luxury of a single path. Different portions of the wavefront are bent and deflected by different pockets of plasma density, effectively splitting the original signal into countless slightly different routes, each with a marginally different length and marginally different travel time. When these routes eventually reconverge at the receiver, they do not arrive as a single clean signal. They arrive as a superposition, an overlapping smear of nearly identical copies of the original message, each shifted slightly in time and phase relative to the others. The result is exactly the ghostly overlap the earlier framing describes, though the mechanism is grounded in real, well-studied plasma physics rather than metaphor. Engineers who work with radio, astronomy, and deep space communication are intimately familiar with this problem, because it also affects our own spacecraft. Signals sent from probes exploring the outer solar system, passing through the Sun's own turbulent corona during certain orbital geometry, experience measurable scattering and timing distortion, a phenomenon that has actually been used by scientists as a tool, allowing them to study the density and structure of the solar wind by observing exactly how much a spacecraft's radio signal gets delayed and smeared as it grazes past the Sun. What is a nuisance for communication becomes, ironically, a scientific instrument. But the underlying distortion is very real and very well documented. It is worth addressing directly why this problem cannot simply be solved with more transmission power, because it might seem intuitive that a sufficiently advanced civilization could simply overpower any amount of interference with a strong enough signal. This intuition while understandable, runs into a hard physical limit. Increasing the power of a transmission increases its strength relative to background noise, which does help in some respects, particularly in distinguishing a real signal from random thermal noise in the receiver. But raw power does not undo the scattering and dispersion imposed by the plasma itself. A stronger signal experiences the same bending, the same splitting into multiple paths, the same smearing across time, because those effects arise from the wave's interaction with the medium's structure, not from any weakness in the original signal. A louder shout does not travel through fog any more clearly than a quiet one. It simply illuminates more of the fog around it. In the same way, a more powerful interstellar transmission does not escape multipath scattering. It merely produces a louder, still scattered echo. This is precisely why the framing of an insurmountable barrier, regardless of a civilization's technological sophistication, holds up under closer scientific scrutiny, at least with respect to certain classes of communication strategy. Any civilization attempting real-time, high-bandwidth radio communication across genuinely interstellar distances, particularly during or near periods of heightened stellar activity, faces the same fundamental physics we do. The laws governing electromagnetic wave propagation through ionized plasma do not care about the technological maturity of the species attempting to bypass them. This does not mean interstellar communication is impossible. It means it is a problem that must be solved through strategy, patience, and clever engineering rather than through raw transmission power alone. An understanding that distinction is essential to understanding what a realistic interstellar communication effort would actually look like. There is also a timing dimension to this problem that deserves attention, because stars do not maintain a constant level of activity throughout their lives. Our own sun follows an activity cycle lasting roughly 11 years, oscillating between quieter periods, called solar minimum, and more turbulent periods, called solar maximum, when flares and coronal mass ejections become dramatically more frequent. During solar maximum, the interstellar medium immediately surrounding a star becomes measurably more disturbed, and any signal attempting to depart or arrive during that window faces significantly higher odds of severe scattering. A civilization transmitting during its home star's quiet phase sends a message with a meaningfully better chance of arriving in a recoverable state than one transmitting during a period of peak stellar turbulence. This means that even the timing of a transmission, not just its content or its power, becomes a critical engineering decision, one that requires understanding your own star's long-term behavior well enough to choose your moments carefully. If a single transmission cannot reliably survive its journey intact, the natural engineering response is redundancy. And this is where the story shifts from pure astrophysics into information theory, the branch of science that studies how reliably information can be transmitted through an imperfect, noisy channel. Information theory was largely founded in the middle of the 20th century by the mathematician and engineer Claude Shannon, whose work established the mathematical foundations still used today to design everything from cell phone networks to deep space communication systems. One of Shannon's central insights was that any communication channel, no matter how noisy, has a maximum rate at which information can be transmitted with an arbitrarily low probability of error. provided the sender uses sufficiently clever encoding. The catch is that achieving that low error rate over a noisy channel almost always requires sending more raw data than the message itself would require in a perfect, noise-free environment, because a portion of that extra data is dedicated to redundancy and error correction rather than new information. This is precisely the situation facing any civilization attempting to send a message through a scattering, dispersive, occasionally storm-disturbed interstellar medium. The raw information content of a greeting, a mathematical sequence, or a description of one's home world might be relatively modest, translatable into a data packet that would take mere seconds to transmit under ideal conditions. But ideal conditions do not exist across light-years of turbulent plasma. To ensure that at least one recoverable, accurately decodable copy of that message survives the journey, engineers must build in substantial redundancy, effectively sending the same core information multiple times, encoded with error-correcting codes that allow the receiver to reconstruct the original message, even if individual portions arrive corrupted, delayed, or overlapping with scattered echoes of themselves. Error-correcting codes are not exotic or speculative technology. They are already a routine part of modern deep space communication, used every time a probe like Voyager, New Horizons, or a Mars rover sends data back to Earth across millions or billions of kilometers of comparatively empty solar system space. Engineers at facilities like the Deep Space Network add carefully designed layers of redundant information to every transmission, allowing ground-based computers to detect and correct errors introduced by the enormous distances, weak signal strength, and background noise these missions must contend with. The famous images returned by the Voyager probes, still transmitting data more than 4 decades after launch from beyond the edge of the solar system, rely heavily on this kind of error correction to arrive as coherent, usable images rather than scrambled static. Interstellar communication would simply require an extraordinarily more aggressive version of the same basic principle, because the distances involved are not measured in billions of kilometers, but in tens of trillions of kilometers. And the medium itself is actively working against the signal in ways that empty solar system space mostly is not. This is the more precise and scientifically grounded version of what the earlier framing calls a bitrate collapse. It is not that the fundamental speed of light itself changes. Light still travels at exactly the same speed, regardless of how much redundancy is encoded into a signal. What collapses is the effective rate at which new, unique information can be reliably extracted at the receiving end. Once you account for how much of the transmitted data must be devoted to redundancy rather than novel content, a message that could theoretically be compressed into a brief burst under perfect conditions might need to be stretched, repeated, and layered with correction codes to the point where the effective, reliably decodable content trickles through at a dramatically slower functional rate, even though every individual bit is still moving at the speed of light. Consider a simplified but illustrative comparison. A message sent between 2 points on Earth using a modern fiber optic cable might carry billions of bits of information every second, because the cable is a controlled, shielded, essentially noise-free environment engineered specifically to preserve signal integrity. A message sent between two star systems separated by dozens or hundreds of light-years, passing through active stellar winds, turbulent interstellar plasma, and periodic coronal mass ejections, might need such extensive redundancy and error correction that the same volume of unique information takes years, decades, or in extreme cases, longer to reliably transmit, even though the raw signal itself is moving at the same universal speed limit. The bottleneck is not the speed of transmission, but the reliability of extraction. And that distinction matters enormously for anyone trying to imagine what an actual interstellar conversation would look like. There is a further complication layered on top of this redundancy requirement, one connected directly back to the solar activity cycles discussed earlier. If a transmitting civilization has learned, as our own understanding suggests it should, that signals sent during a star's quieter phase have a meaningfully better chance of arriving intact, then the most efficient strategy is not to transmit continuously, but to concentrate transmission efforts during those calmer windows, essentially timing bursts of redundant, error-corrected data to coincide with periods of reduced stellar turbulence. Because stellar activity cycles for sun-like stars often span roughly a decade, and because both the sending star system and the receiving star system have their own independent activity cycles that may or may not align favorably, the practical result is a communication strategy built around patient, infrequent, heavily redundant bursts rather than a steady, real-time stream. A single, complete, reliably reconstructible message might genuinely require the accumulated data from multiple transmission windows, spread across years or decades, before a receiving civilization has gathered enough overlapping, error-corrected copies to confidently reconstruct the original content. This picture reframes what interstellar communication would actually feel like for any civilization patient enough to attempt it. It would not resemble a telephone call with its expectation of immediate, continuous, two-way exchange. It would resemble something closer to a message in a bottle, sent out with enormous care and redundancy, cast into a turbulent sea, with the sender fully aware that any reply, if one comes at all, will not arrive for years or decades, and that the reply itself will need to survive the exact same gauntlet of scattering, dispersion, and stellar interference on its own return journey. Every stage of the exchange, from initial transmission through eventual reception and any subsequent reply, is stretched across timescales that dwarf a single human lifetime, turning what might begin as an eager, curious first contact attempt into a project that must be handed down across generations of scientists, engineers, and institutions simply to see it through to its conclusion. It is worth pausing on that image for a moment, because it reshapes the entire question of what patience actually means on a cosmic scale. And if that reframing changes how you think about our own place in this slow, unfolding conversation, it is worth carrying that thought forward into everything that follows. This generational aspect is not merely a poetic observation. It carries real institutional and engineering implications. A civilization committed to interstellar communication under these conditions would need to build infrastructure, training programs, and archival systems capable of maintaining continuity of purpose across decades or centuries, ensuring that the scientists who eventually receive and analyze a returning signal understand precisely what was sent, why it was sent, and how to properly decode and interpret whatever partial, redundant, storm-scattered fragments eventually arrive. It is a communication strategy that demands not just technological sophistication, but a kind of institutional patience that very few human projects have ever needed to sustain. Closer in spirit to the great cathedrals that took generations to complete than to any modern research program measured in annual funding cycles, this reframing has already begun to influence how scientists studying the search for extraterrestrial intelligence think about their own methods, even in the absence of any confirmed detection. For most of the history of the field, the dominant search strategy has been what researchers sometimes call the real-time listening model, in which large radio telescopes scan wide portions of the sky, looking for a signal strong and clean enough to stand out clearly during a relatively brief observation window, often lasting only minutes for any given patch of sky before the telescope moves on to survey another region. This approach made sense as an efficient way to cover as much of the sky as possible with limited observing time, and it has genuinely been successful at ruling out certain classes of powerful, continuously broadcasting signals across large portions of the galaxy. But it is poorly suited to detecting the kind of faint, scattered, heavily redundant, intermittently transmitted signal that the physics discussed so far suggests might be far more realistic. A growing number of researchers have begun advocating for what might be called long-term signal integration, a fundamentally different philosophy that treats detection not as a single decisive moment, rather than requiring a signal to be strong and clean enough to stand out during a brief scan. This approach involves repeatedly observing the same patch of sky, or the same candidate star system, over extended periods, sometimes years, deliberately accumulating faint, partial, individually inconclusive data and combining it using sophisticated statistical and computational techniques to search for patterns that would be invisible in any single observation but become statistically significant once enough overlapping data has been gathered. This is conceptually similar to how astronomers detect extremely faint, distant galaxies by combining dozens or hundreds of individual exposures from a telescope like the Hubble Space Telescope, each exposure too faint and too noisy to reveal much on its own, but together, through careful stacking and processing, revealing structures that would otherwise remain completely invisible. Applying this same philosophy to the search for artificial interstellar signals requires a substantial shift in both hardware and mindset. Modern radio telescope arrays increasingly incorporate this kind of long baseline data accumulation as a matter of course, storing raw observational data for extended periods specifically so that improved processing algorithms, developed years later, can be applied retroactively, effectively allowing scientists to search old data with new tools, uncovering patterns and signals that earlier, less sophisticated analysis techniques would have missed entirely. This means the search for extraterrestrial intelligence is not solely a matter of building bigger, more sensitive telescopes, though that certainly helps, but also a matter of building better long-term data archives and smarter algorithms capable of finding a coherent signal buried within years of accumulated, individually unremarkable noise. The engineering challenge here is genuinely difficult, and it goes well beyond simply storing more data. A receiver attempting to reconstruct a heavily redundant, multipath scattered signal spread across years of intermittent transmission bursts must solve something analogous to an enormous, multi-dimensional puzzle, correlating fragments of data that may have arrived months or years apart, each fragment individually corrupted by different amounts of dispersion and scattering depending on the exact solar and interstellar conditions present at the moment it was received. Modern advances in computational processing power and statistical signal analysis have made this kind of reconstruction far more feasible than it would have been even 2 decades ago. But it remains a computationally intensive, methodologically demanding process, one that requires not just powerful hardware, but carefully validated techniques for distinguishing genuine, reconstructible signal patterns from the countless false positives that inevitably emerge when searching for faint patterns within enormous volumes of noisy data. This shift in strategy also changes how scientists think about what a successful detection would actually look like. And this is where the redefinition of first contact becomes genuinely significant. The popular cultural image of first contact, heavily shaped by decades of science fiction, tends to imagine a dramatic, singular moment, a signal detected, decoded, and understood within days or weeks, followed by an exchange of ideas unfolding at a pace recognizable to a human audience, accustomed to conversations that happen in real time. The physics discussed throughout this exploration suggests a very different, far less cinematic reality. A genuine detection, if one occurs, would more likely resemble the slow, patient accumulation of statistical confidence, in which scientists spend years gathering, correlating, and cross-checking faint, fragmented data before feeling justified in declaring that a signal is very likely artificial rather than a natural astrophysical phenomenon or an instrumental error. Even after that threshold of confidence is reached, actually decoding the content of the message, assuming it contains encoded information rather than simply serving as a detectable beacon, would represent an entirely separate and potentially far longer undertaking. Every layer of redundancy and error correction built into the original transmission by its senders, all of which is necessary precisely because of the scattering and dispersion discussed earlier, must be correctly identified and reversed by the receiving civilization, without any prior knowledge of what encoding scheme was used or what conventions the senders assumed their eventual audience would understand. This is a genuinely difficult problem, even in principle, related to a long tradition of thinking within the search for extraterrestrial intelligence community about how to design messages that could be understood by a civilization with no shared language, no shared cultural references, and only mathematics and physics as a plausible common ground. The Arecibo message, transmitted in 1974 toward a distant star cluster as a demonstration of the newly upgraded Arecibo radio telescope's capabilities, remains one of the most famous attempts to grapple with this problem directly, encoding basic information about human biology, our solar system, and the transmitting technology itself using a simple binary format designed to be interpretable, using nothing more than mathematics as a shared foundation. That message will not arrive at its target for tens of thousands of years. a timescale that itself illustrates just how patient any genuine interstellar communication effort must be willing to be. If a comparable message sent by a distant civilization were to reach Earth, successfully decoding it would likely require exactly the kind of patient, collaborative, multi-generational scientific effort now being contemplated by researchers thinking seriously about long-term signal integration. What emerges from this reframing is a definition of successful first contact that looks far less like a single triumphant announcement and far more like an extended collaborative marathon, stretched across years of data collection, cross-validation, and careful decoding, likely involving multiple independent research teams working to confirm and interpret the same signal before any confident public announcement could responsibly be made. This is not a pessimistic conclusion, even though it lacks the drama of popular depictions. It is, in many ways, a more scientifically honest and ultimately more hopeful picture, because it suggests that the absence of a dramatic, immediate detection so far does not mean no one out there is transmitting, and does not mean our own transmissions are necessarily failing to reach anyone. It may simply mean that the true nature of interstellar contact, if it ever happens, will unfold on a timescale and in a manner very different from what earlier generations of researchers and earlier generations of storytellers originally imagined, given everything described so far. The practical question becomes how a civilization, ours included, might actually design an outgoing interstellar signal capable of surviving this gauntlet with the highest possible chance of success. This is not a purely theoretical exercise. Engineers and physicists working on real proposals for interstellar communication and interstellar probes, including modern successors to the thinking behind the Voyager golden records and the Arecibo message, have already begun incorporating lessons drawn from exactly the kind of plasma, physics, and information theory discussed throughout this exploration. The first and most obvious lesson involves error correction, sophisticated enough to anticipate not just random background noise, but the specific, structured kind of distortion introduced by dispersion, scintillation, and multipath scattering. Modern coding theory has produced increasingly powerful families of error-correcting codes, including techniques originally developed for deep space missions and later adapted for use in everyday technologies like compact discs, satellite television, and mobile phone networks. Codes capable of correcting not just isolated, randomly scattered errors, but entire bursts of consecutive corrupted data are particularly relevant here, because the kind of scattering produced by turbulent interstellar plasma tends to corrupt data in exactly this clustered, burst-like pattern, rather than as isolated, randomly distributed errors. A sophisticated interstellar protocol would almost certainly need to layer multiple types of error correction together, some designed to handle scattered individual errors and others specifically designed to handle the larger structured distortions introduced by scintillation and multipath interference. The second major lesson involves timing strategy, deliberately choosing when to transmit based on known patterns of stellar activity. A civilization aware of its own star's activity cycle, and ideally aware of the target star's activity cycle as well, gains a meaningful advantage by concentrating transmission efforts during quieter periods for both systems, when possible. minimizing the additional scattering introduced by active coronal mass ejections and intense flares on either end of the journey. This kind of careful timing does not eliminate the underlying challenge posed by the interstellar medium itself, but it meaningfully improves the odds that any given transmission burst arrives in a more recoverable state, effectively stacking the deck in favor of successful reconstruction at the receiving end. The third and perhaps most conceptually striking lesson involves an entirely different physical strategy for concentrating a signal's strength, one that moves beyond simply boosting transmission power or adding redundancy and instead exploits gravity itself as a natural amplifying lens. This is the idea behind what physicists call the solar gravitational lens, a genuinely real and actively studied phenomenon rooted directly in Einstein's general theory of relativity. According to general relativity, mass bends the path of light and other electromagnetic radiation passing near it, an effect first dramatically confirmed during a solar eclipse observation in 1919, when starlight passing near the Sun was measured to bend by precisely the amount Einstein's equations predicted. Because our Sun's own mass bends light in this way, there exists a specific region of space far beyond the orbit of Pluto, at roughly 550 times the distance between the Earth and the Sun, where light and radio waves from a distant target, passing on the opposite side of the Sun, converge and are dramatically amplified, in principle by factors reaching into the tens of billions, simply due to the geometry of gravitational lensing. Physicists studying this phenomenon have proposed that a spacecraft positioned precisely at this gravitational focal point could use the Sun itself as an enormous natural lens, dramatically amplifying either an outgoing transmission aimed toward a distant star system or an incoming signal received from that same direction, far beyond what any conventional antenna, no matter how large, could achieve on its own. This concept remains firmly in the realm of proposed, not yet realized, technology, since positioning and maintaining a functioning spacecraft precisely at that focal distance, and keeping it aligned accurately enough to exploit the lensing effect for a specific target star, represents an enormous engineering challenge involving distances and precision requirements, well beyond anything achieved by any spacecraft launched to date. Multiple space agencies and independent research groups have nonetheless published detailed technical studies exploring exactly how such a mission might work, treating it as a serious long-term goal rather than pure speculation, precisely because the potential gains in signal strength are so dramatic that they could meaningfully offset much of the scattering and dispersion loss discussed. Throughout this exploration, it is worth being precise about what gravitational lensing can and cannot solve. Amplifying a signal's raw strength at the point of transmission or reception does not eliminate the scattering and dispersion that occurs as the signal crosses the turbulent interstellar medium in between. A dramatically amplified signal still passes through the same fog, still experiences the same multipath splitting, still requires the same kind of redundant, error-corrected encoding to be reliably reconstructed at the other end. What gravitational lensing offers is a way to ensure the signal begins its journey, or is captured at its destination, with dramatically more raw strength than would otherwise be possible. effectively giving the message a much larger safety margin to work with, as it inevitably loses coherence along the way. It is a powerful complement to, rather than a replacement for, the redundancy and timing strategies already discussed. Taken together, these three strategies, layered error correction, anticipating structured plasma distortion, careful timing aligned with stellar activity cycles, and gravitational lensing to maximize raw signal strength, begin to sketch out what a genuinely realistic interstellar communication protocol might actually look like. It is a strategy built not around brute force, but around a deep, patient understanding of the physical environment a signal must survive, treating the challenge less like sending a simple message and more like designing a message specifically engineered to endure a known, well-characterized, but genuinely hostile journey. This is arguably the deeper significance behind framing the challenge as a final test facing any civilization attempting to join a broader galactic community, if such a community exists at all. Surviving long enough as a technological species to attempt interstellar communication is itself an extraordinary achievement, requiring a civilization to avoid self-destruction through war, environmental collapse, or any number of other existential risks, long enough to develop the scientific and technological capacity for the attempt in the first place. But surviving as a species is not sufficient on its own. A civilization must also develop the patience, the institutional continuity, and the sophisticated understanding of plasma physics and information theory necessary to design a message capable of actually surviving its journey through the turbulent, storm-scattered medium separating one star system from another. In this sense, mastering the game of whispers is not simply an engineering hurdle. It is a genuine test of a civilization's long-term thinking, its scientific maturity, and its willingness to invest enormous resources and patience into a project whose payoff, if it comes at all, may not arrive for many generations. To fully appreciate how significantly this understanding of interstellar plasma physics has reshaped the search for extraterrestrial intelligence, it helps to trace the field's history from its earliest scientific foundations. The modern search effectively began in 1959, when physicists Giuseppe Cocconi and Philip Morrison published a paper in the journal Nature arguing that radio waves represented the most plausible medium for interstellar communication, given their ability to travel enormous distances with comparatively little energy loss and their compatibility with the technology already being developed for radio astronomy at the time. Their paper proposed that any civilization attempting to signal its presence across interstellar space would likely choose a recognizable, mathematically significant frequency, and they specifically suggested the frequency corresponding to the emission of neutral hydrogen, the most abundant element in the universe, reasoning that any sufficiently advanced civilization studying the cosmos would already be familiar with this particular frequency from their own astronomical observations. Independently and almost simultaneously, the astronomer Frank Drake began the first practical search effort, a project named Ozma, conducted in 1960 using a radio telescope in West Virginia to listen for artificial signals from two nearby sun-like stars. Project Ozma detected nothing conclusive, but it established the basic observational template that countless subsequent searches would follow. listening carefully at specific frequencies for signals distinct from the natural background noise produced by stars, gas, clouds, and other astrophysical sources. Drake later formalized the broader question of how many communicating civilizations might exist in our galaxy through what has become known as the Drake equation, a framework that breaks the question down into a series of factors, including the rate of star formation, the fraction of stars hosting planets, the fraction of those planets capable of supporting life, and the average lifetime of a civilization capable of interstellar communication. The Drake equation was never intended as a precise predictive formula, since many of its factors remain deeply uncertain even today, but it succeeded in reframing an overwhelming philosophical question into a structured, scientifically tractable set of smaller questions, each of which subsequent decades of astronomy have gradually chipped away at with real observational data. The discovery of thousands of confirmed exoplanets over the past 3 decades, beginning with the first confirmed detection of a planet orbiting a sun-like star in 1995, has dramatically narrowed the uncertainty around several of the equation's early terms, revealing that planets are common companions to stars throughout the galaxy rather than a rare cosmic accident. What remains far more uncertain and far more relevant to everything discussed throughout this exploration is the equation's final term, the average lifetime of a communicating civilization, a factor deeply entangled with exactly the kind of physical and engineering challenges posed by the interstellar medium's turbulent, storm-scattered nature. This is where the physics discussed throughout this exploration connects to one of the most persistent and unsettling puzzles in the entire search for extraterrestrial intelligence. A puzzle known as the Fermi paradox, named after the physicist Enrico Fermi, who reportedly posed a simple but pointed question during a 1950 casual lunch conversation with colleagues, essentially asking that if intelligent civilizations are common throughout the galaxy, where is everybody? Given the galaxy's age, roughly 13 billion years, and the comparatively short timescales on which a sufficiently motivated civilization could theoretically spread probes or signals across significant portions of the galaxy, the complete absence of any confirmed detection has struck many researchers as genuinely puzzling, prompting decades of proposed explanations ranging from the mundane to the deeply speculative. Some proposed explanations suggest that intelligent, technological civilizations are simply extraordinarily rare, perhaps due to the difficulty of specific evolutionary transitions, such as the emergence of complex multicellular life or the development of sufficiently sophisticated intelligence and tool use. Other explanations suggest that civilizations are common but tend to be destroying themselves through war, environmental collapse, or other existential risks before developing the capacity for interstellar communication or travel. Still others suggest that civilizations exist and persist but simply have not yet had time or motivation to reach out across the specific portion of the galaxy containing our own solar system. The physics of interstellar signal degradation discussed throughout this exploration offers a distinct and comparatively underappreciated addition to this list of possible explanations, one that does not require assuming civilizations are rare, short-lived, or uninterested in communication. It suggests instead that the physical difficulty of the communication problem itself may be a significant contributing factor, entirely independent of how common or how motivated communicating civilizations actually are. If successfully sending or receiving an interstellar message requires the kind of sophisticated, patient, multi-generational engineering effort described throughout this exploration, then even a galaxy filled with numerous communicating civilizations might produce remarkably few detectable, decodable signals at any given moment, simply because the physical and engineering barriers involved are so substantial. This does not resolve the Fermi paradox on its own, but it adds meaningful nuance to how researchers think about the absence of detected signals, shifting some of the explanatory weight away from questions about the rarity or behavior of civilizations and toward questions about the sheer physical difficulty of the communication channel itself. Modern efforts to search for extraterrestrial signals have evolved considerably from the single telescope, single frequency approach used in Project Ozma more than 6 decades ago. The non-profit SETI Institute, founded in the 1980s, has spent decades developing increasingly sophisticated search strategies and instruments, including the Allen Telescope Array in Northern California, a facility specifically designed to allow simultaneous observation across a wide range of frequencies rather than the narrow, single-frequency searches of earlier decades. This broader frequency coverage directly addresses part of the challenge posed by interstellar scattering, since different frequencies experience different amounts of dispersion and scintillation as they pass through turbulent plasma, meaning that a signal severely degraded at one frequency might remain comparatively more recoverable at another. An even more ambitious effort, Breakthrough Listen, launched in 2015 with substantial private funding, represents the most comprehensive search for extraterrestrial signals ever undertaken, using some of the world's largest and most sensitive radio telescopes to survey 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies, while also systematically archiving enormous volumes of raw observational data for exactly the kind of long-term, retroactive analysis discussed earlier in this exploration. This archival approach directly reflects the shift toward long-term signal integration, acknowledging that today's analysis techniques may miss patterns that tomorrow's more sophisticated algorithms could successfully identify within the same underlying data. Looking toward the future, an international collaboration is currently constructing the Square Kilometre Array, a next-generation radio telescope project spanning sites in South Africa and Australia, designed to combine signals from thousands of individual antennas into a single instrument with sensitivity and resolution far exceeding any radio telescope built to date. Once fully operational, this kind of instrument will offer astronomers dramatically improved tools for both detecting extremely faint signals and, crucially, for better characterizing the structure and turbulence of the interstellar medium itself, directly improving scientists' ability to model and eventually compensate for exactly the kind of scattering and dispersion discussed throughout this exploration. Better characterization of interstellar turbulence does not eliminate the underlying physical challenge, but it does allow researchers to develop more sophisticated correction algorithms, effectively learning the specific distorting fingerprint of a given patch of sky well enough to partially reverse its effects during data analysis. Researchers are also exploring communication strategies beyond traditional radio frequencies, recognizing that different parts of the electromagnetic spectrum experience the interstellar medium's turbulence differently. Optical searches, looking for brief, powerful pulses of laser light rather than radio waves, have expanded considerably over the past 2 decades, partly because laser light at certain wavelengths experiences less dispersion and scattering from ionized plasma than lower frequency radio waves do, though optical signals introduce their own distinct challenges, including much narrower beam widths that require far more precise aiming at an intended target. Some researchers have proposed that a truly sophisticated interstellar protocol might use multiple frequencies simultaneously, spanning both radio and optical wavelengths, precisely because different frequencies are vulnerable to different aspects of interstellar turbulence, giving a multi-frequency message a better overall chance that at least one component arrives in a recoverable state. Even if others are severely degraded, this growing sophistication extends beyond passive listening strategies into active consideration of how humanity's own outgoing signals, both deliberate and incidental, might be perceived by any civilization capable of detecting them. Earth has been an increasingly loud radio source since the early 20th century, with television broadcasts, radar systems, and radio communication leaking outward into space as an unintentional byproduct of our own technological development. Though this incidental leakage tends to be far weaker and far less structured than a deliberately engineered interstellar transmission would be, and it is subject to the exact same scattering and dispersion effects discussed throughout this exploration as it travels outward. Some researchers have specifically modeled how Earth's incidental radio leakage would appear to a hypothetical civilization at various distances, factoring in realistic interstellar medium turbulence, and have generally concluded that our accidental broadcasts become extremely difficult to detect and even more difficult to meaningfully decode beyond a relatively modest distance, reinforcing just how much more deliberate, redundant, and carefully engineered any genuinely intentional interstellar message would need to be compared to our incidental technological noise. This raises an important implication for how humanity thinks about its own visibility to the wider galaxy, one connected to ongoing scientific and ethical debates about whether deliberately transmitting a message announcing our presence, sometimes called active search for extraterrestrial intelligence, represents a wise or a risky strategy. Some researchers have expressed concern that broadcasting our presence and location to unknown civilizations could carry unforeseen risks, while others argue that our accidental radio leakage has already made our presence at least partially detectable to any sufficiently advanced and attentive nearby observer, and that the physics of interstellar scattering discussed throughout this exploration means any truly distant civilization would need an extraordinarily sensitive, patient search strategy to notice us at all under current conditions. This debate remains unresolved within the scientific community without a clear consensus, and it illustrates how the physical realities of interstellar signal propagation feed directly into genuinely difficult questions about strategy, risk, and humanity's own role as both a potential listener and a potential transmitter within this larger cosmic conversation. The implications of this research extend well beyond the specific question of detecting or sending messages to distant civilizations, touching on several other active areas of astrophysics and space science in ways that reinforce just how fundamental these plasma physics principles are to our broader understanding of the universe. Fast radio bursts, an entirely natural astrophysical phenomenon first identified in 2007, provide one particularly striking real-world example of exactly the kind of dispersion discussed throughout this exploration, playing out on a genuinely cosmic scale. These extraordinarily brief, extraordinarily powerful bursts of radio energy, lasting only milliseconds, but releasing more energy in that brief flash than our sun produces over an entire day, originate from sources still not completely understood, though many appear to be connected to magnetar, a rare and extreme class of neutron star possessing magnetic fields trillions of times stronger than Earth's own. What makes fast radio bursts particularly relevant to this exploration is that astronomers studying them rely directly on measuring dispersion, the exact same frequency-dependent delay discussed earlier in the context of pulsar, to estimate how far a given burst has traveled and how much ionized material it passed through along the way. Because fast radio bursts often originate from galaxies billions of light-years away, far more distant than anything a deliberate interstellar message would need to travel, they offer astronomers an extraordinarily useful natural laboratory for studying how electromagnetic signals behave after crossing vast cosmic distances filled with turbulent ionized material, directly refining the same physical models and mathematical tools relevant to understanding how any hypothetical artificial interstellar signal would behave under similar conditions. In this sense, ongoing research into a completely natural, unrelated astrophysical mystery has quietly become one of the most valuable sources of real-world data informing scientists' understanding of exactly the communication challenges discussed. Throughout this exploration, this research also has direct, practical relevance to humanity's own ongoing space exploration efforts, well beyond the speculative question of contacting other civilizations. Every spacecraft currently operating beyond Earth's immediate vicinity, from Mars rovers to the Voyager probes now traveling through interstellar space itself, depends on engineers correctly modeling and compensating for exactly the kinds of signal degradation discussed throughout this exploration, adjusting transmission power, encoding schemes, and timing based on real-time monitoring of solar activity and the current state of the interplanetary and interstellar medium. Space weather forecasting, an increasingly sophisticated field dedicated to predicting solar flares and coronal mass ejections before they occur, has become directly relevant not just to protecting satellites and power grids here on Earth, but to planning reliable communication windows for humanity's growing fleet of deep space missions, a practical, immediate application of exactly the same underlying physics discussed throughout this exploration in its more speculative, extraterrestrial context. Voyager 1, launched in 1977, and now the most distant human-made object in existence, having crossed the boundary of the heliosphere into true interstellar space in 2012, offers a genuinely remarkable real-world test case for many of these principles. Communication with Voyager 1 now requires signals to travel more than 22 billion kilometers, taking over 20 hours to reach the spacecraft one way, and engineers at the Deep Space Network must account for exactly the kind of signal weakening and interference discussed throughout this exploration, though at a scale still dramatically smaller than genuine interstellar distances between separate star systems. The fact that Voyager 1 continues to return usable scientific data more than 4.5 decades after launch stands as a powerful testament to the effectiveness of careful engineering, redundant encoding, and patient, adaptive communication strategy. Even though its distance remains a vanishingly small fraction of the distance separating our solar system from even the nearest neighboring star system, researchers have also begun exploring whether entirely different physical carriers of information beyond conventional electromagnetic radiation might eventually offer alternative pathways around some of the challenges discussed throughout this exploration. Neutrinos, extraordinarily lightweight subatomic particles, capable of passing through enormous amounts of matter with virtually no interaction, have occasionally been proposed as a theoretically interesting alternative communication carrier, precisely because their almost complete lack of interaction with ordinary matter and plasma means they would experience essentially none of the dispersion, scattering, or scintillation effects discussed throughout this exploration. This same property, however, makes neutrinos extraordinarily difficult to detect and to generate in a sufficiently strong, directed beam using any currently foreseeable technology, and serious proposals for neutrino-based interstellar communication remain firmly speculative, discussed more as an interesting theoretical possibility than a practical near-term alternative to conventional electromagnetic signaling. Gravitational waves, ripples in space-time itself, first directly detected in 2015, have received similar speculative interest for related reasons, since they too would pass through ordinary plasma with negligible interaction, though generating a deliberately encoded gravitational wave signal strong enough to be detected across interstellar distances remains far beyond any technology currently available or seriously proposed, despite the substantial progress made across all these fronts, from improved theoretical models of plasma turbulence to increasingly sensitive telescopes and increasingly sophisticated data archives. A great deal remains genuinely uncertain, and it is worth being honest about the scale of what scientists still do not know. The precise, detailed structure of the interstellar medium along most specific lines of sight remains poorly mapped, particularly for the vast majority of nearby star systems that have not been the subject of intensive, targeted study. Researchers can estimate general trends, average densities, and typical turbulence levels across broad regions of the galaxy, but predicting exactly how severely a signal would be scattered along any single specific path toward any single specific candidate star system remains difficult, limited by the availability of detailed observational data along that precise line of sight. Scientists also do not yet have a complete, unified theoretical model capable of fully predicting how multipath scattering and dispersion interact with realistic Sophisticated error-correcting codes under the enormous range of conditions a genuine interstellar signal might encounter. Much of the theoretical work in this area, while grounded firmly in well-established plasma physics and information theory, still relies on simplified models and computer simulations rather than direct observational confirmation, simply because no one has yet attempted a genuine interstellar transmission and reception experiment across the kind of true interstellar distances discussed throughout this exploration. Voyager 1, despite being humanity's most distant transmitting object, remains firmly within what astronomers still consider the very near edge of interstellar space, still deeply influenced by our own sun's magnetic field and solar wind, and still nowhere close to the kind of multi-light-year journey a genuine interstellar message to another star system would require. This absence of direct experimental confirmation across truly interstellar distances represents one of the field's most significant open challenges, and it is unlikely to be resolved anytime soon, given the enormous timescales involved in any experiment that would require actually sending and receiving a signal across even the nearest neighboring star system. Researchers have instead focused on indirect confirmation, using natural phenomena like pulsars and fast radio bursts as proxies, studying how these naturally occurring signals behave after crossing genuinely vast interstellar and even intergalactic distances, and using those observations to refine and validate the same underlying physical models relevant to hypothetical artificial signals. This indirect approach has proven remarkably productive, but it inevitably leaves some open questions that only a genuine, deliberate interstellar communication attempt, sustained across the necessary decades or centuries, could ultimately resolve with full confidence. There also remains substantial uncertainty regarding how a genuinely advanced, technologically mature civilization might choose to solve these problems, using engineering approaches not yet seriously considered by human scientists and engineers. Everything discussed throughout this exploration reflects the current state of human scientific and technological understanding, grounded in well-established physics, but necessarily limited by the boundaries of what human engineers have actually developed and tested. A civilization with access to technologies far beyond anything currently available to humanity might have developed entirely different solutions to the challenges posed by interstellar scattering and dispersion, solutions that current human science cannot yet anticipate or model with any confidence. This is not a criticism of the scientific approach described throughout this exploration, but rather an honest acknowledgement of its inherent limitation. An acknowledgement that responsible scientists studying this question consistently emphasize when discussing the broader implications of their work. Researchers continue to actively investigate several promising directions that may substantially improve our understanding over the coming years and decades. Improved computational modeling, drawing on ever-increasing processing power, allows scientists to simulate increasingly realistic, increasingly detailed models of turbulent interstellar plasma, testing how various proposed encoding and error correction strategies would theoretically perform under a wide range of simulated conditions before any real transmission is ever attempted. Continued observation and analysis of fast radio bursts and pulsars, particularly using next-generation instruments like the Square Kilometre Array once it becomes fully operational, promises to substantially refine scientists' empirical understanding of how electromagnetic signals actually behave after crossing genuinely vast, genuinely turbulent cosmic distances, providing an ever-improving real-world foundation for the theoretical models discussed. Throughout this exploration, serious engineering studies into the Solar Gravitational Lens mission concept continue to advance as well, with research teams refining proposed spacecraft designs, propulsion strategies capable of reaching the required distance within a reasonable mission timeframe, and precision positioning techniques necessary to actually exploit the gravitational amplification effect for a specific target star system. While no mission of this kind has yet been formally approved or funded for launch, the sustained, serious technical interest from multiple research groups suggests this concept will likely remain an active area of study and refinement for years to come, representing one of the most concrete, technically grounded paths toward eventually testing many of the ideas discussed throughout this exploration under genuinely realistic conditions. There is something clarifying about placing this challenge alongside earlier chapters of human communication history, because humanity has actually faced strikingly similar problems before, albeit on vastly smaller scales, and the solutions developed then offer genuine insight into the solutions likely required now. Consider the first attempts to lay a telegraph cable across the floor of the Atlantic Ocean in the 1850s, an engineering effort that pushed the absolute limits of available materials, science, and electrical theory at the time. Early transatlantic cables suffered from severe signal degradation. Electrical current traveling through thousands of kilometers of cable experienced smearing and distortion strikingly analogous, in a rough conceptual sense, to the dispersion and scattering discussed throughout this exploration, though the underlying physics involved completely different phenomena related to the cable's electrical capacitance rather than plasma turbulence. Messages that should have taken minutes to transmit sometimes took hours to reliably decode, and the first successful cable, completed in 1858, functioned only briefly before failing entirely, requiring nearly a decade of further engineering refinement before a reliable, durable transatlantic connection was finally established in 1860. The engineers who eventually solved the transatlantic cable problem did so not by simply pumping more electrical power through the line, an approach that had already been tried and had actually worsened the distortion in earlier attempts, but through a more sophisticated understanding of the underlying physics, leading to redesigned cables, improved insulation materials, and more careful, patient signaling protocols specifically engineered to work within the cable's real physical limitations rather than fighting against them. This same pattern echoes directly through everything discussed throughout this exploration regarding interstellar communication, where brute force power alone cannot overcome the fundamental physics of the medium, and genuine progress requires working intelligently within the constraints that medium imposes, rather than attempting to simply overpower them. An even more directly relevant historical parallel involves humanity's own deliberate attempts to send physical rather than electromagnetic messages toward the stars. The Pioneer plaques, attached to the Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, and the more elaborate Voyager golden records, attached to both Voyager probes, launched in 1977, represent humanity's first deliberate attempts to craft a message intended for a potential audience separated from us, not just by enormous distance, but by complete cultural and biological unfamiliarity. These physical messages sidestep the electromagnetic scattering problem entirely, since they are carried aboard a physical spacecraft rather than transmitted as a radio or optical signal. But the spacecraft themselves travel so slowly, even at their considerable velocity, that they will not pass anywhere near another star system for tens of thousands of years, illustrating yet another way in which any genuine attempt at interstellar contact, whether through physical objects or electromagnetic signals, inevitably operates on timescales that dwarf any single human lifetime. The team responsible for designing the Voyager golden records, led by the astronomer Carl Sagan, grappled directly with many of the same fundamental questions discussed throughout this exploration regarding how to encode a message that could survive not just the physical journey, but the interpretive challenge of being understood by an audience with no shared language or cultural context. Their solution involved relying heavily on mathematics, basic physics, and carefully chosen diagrams intended to be interpretable using logic and reasoning alone. A philosophy directly analogous to the error correction and encoding strategies discussed earlier in this exploration. Both approaches ultimately reflecting the same underlying insight, that a message intended to survive an enormous journey toward an unknown, unfamiliar recipient must be built around principles robust enough to survive significant loss of context and clarity along the way. Whether that loss comes from physical deterioration, cultural unfamiliarity, or, in the case of electromagnetic signals, the turbulent scattering of the interstellar medium itself. These historical parallels reinforce a theme that runs throughout this entire exploration, that the challenges posed by interstellar distance and interstellar turbulence are not entirely without precedent in human experience, even if their scale is genuinely unprecedented. Every previous generation that has attempted to communicate across enormous distances and enormous spans of time, from ancient civilizations burying time capsules intended for descendants centuries later, to 19th-century engineers wrestling with the physics of transatlantic cables, to 20th-century scientists designing messages intended for an audience that might not exist for tens of thousands of years, has grappled with some version of the same fundamental problem: how to build something robust enough, redundant enough, and thoughtfully enough designed to survive a journey whose full difficulty cannot be entirely anticipated in advance. Interstellar communication simply represents the most extreme version of this ancient and recurring human challenge, stretched across distances and timescales that make even the most ambitious historical precedents look modest by comparison. This broader perspective also reshapes how we might think about humanity's own realistic near-term and long-term strategy regarding interstellar communication, moving the conversation away from science fiction fantasies of imminent conversation and toward a more grounded, incremental set of achievable milestones. In the near term, continued investment in better mapping the interstellar medium's structure and turbulence, particularly along the lines of sight toward the most promising nearby candidate star systems already identified through exoplanet surveys, would substantially improve scientists' ability to model exactly what kind of signal degradation any future transmission or reception attempt toward those specific targets would likely encounter. This kind of targeted mapping work is already underway in a limited form, but it remains far from complete, and expanding it represents one of the most immediately actionable steps available to researchers working in this field today. In the medium term, continued refinement of error-correcting codes specifically optimized for the structured, burst-like distortion patterns characteristic of plasma scattering, rather than the more generic random noise most error-correcting codes were originally designed to handle, represents another concrete area where meaningful progress seems achievable within the coming decades. Building directly on decades of existing deep space communication experience already accumulated through missions like Voyager, New Horizons, and the growing fleet of Mars exploration spacecraft, engineers working on these existing missions already grapple with signal degradation across solar system distances, and much of that accumulated practical experience translates directly, if scaled up considerably, into the kind of protocol design that a genuine interstellar transmission would require. In the longer term, serious development of the solar gravitational lens mission concept, along with continued expansion of long-term signal integration search strategies using increasingly powerful and increasingly well-archived radio telescope data, represents the most technically credible path toward eventually testing many of the theoretical ideas discussed throughout this exploration under genuinely realistic conditions. Even if any actual attempt at interstellar transmission or detection remains, by its very nature, a project whose ultimate resolution would likely unfold across multiple human generations, rather than within the career span of any single researcher who begins the work. This generational framing, uncomfortable as it may feel within a scientific culture often oriented around comparatively short funding cycles and may ultimately represent one of the most important shifts in perspective required to make genuine progress on this problem. Institutions capable of maintaining consistent scientific purpose, careful data archiving, and accumulated technical knowledge across many decades, rather than relying on any single research group or funding cycle, appear far better suited to eventually succeeding at this kind of challenge than any approach built around the expectation of a rapid, individually attributable breakthrough. Some research institutions and space agencies have already begun explicitly incorporating this kind of long-term institutional thinking into how they plan and fund search efforts, treating data archiving and methodological continuity as seriously as they treat the development of new hardware, precisely because the physics discussed throughout this exploration makes clear that patience and continuity may matter every bit as much as raw technological sophistication. There is also a quieter, more philosophical dimension to this reframing worth acknowledging directly. A search and communication strategy built around patience, redundancy, and generational continuity asks something different of the scientists and institutions involved than a strategy built around the expectation of rapid, individually attributable success. It asks researchers to find meaning and motivation in contributing to a project whose ultimate resolution they personally may never witness, trusting that future generations, equipped with better tools, more refined models, and decades of carefully archived data, will eventually carry the work to whatever conclusion it reaches. This is, in its own way, a profound expression of scientific optimism, a willingness to invest serious effort into a question precisely because it matters, regardless of whether the investing generation personally receives the answer. It is worth taking a closer, more technical look at exactly how astronomers quantify and characterize this interstellar turbulence, because the mathematical tools involved reveal just how deeply this problem is embedded in fundamental plasma physics, rather than being any kind of loosely defined or speculative concept. Researchers studying the turbulent structure of ionized interstellar gas commonly describe it using what is called a Kolmogorov turbulence spectrum, a mathematical framework originally developed in the 1940s by the Soviet mathematician Andrei Kolmogorov to describe turbulent fluid flow in far more mundane, everyday contexts, such as water flowing through a pipe or air moving across an airplane wing. Remarkably, the same basic mathematical structure that describes how large-scale turbulent eddies break down into progressively smaller ones within an ordinary fluid also describes, with impressive accuracy, how density fluctuations within the ionized interstellar medium, from enormous structures spanning many light-years down to comparatively tiny irregularities only a few hundred kilometers across. This universality is not merely a mathematical curiosity. It has direct practical consequences for predicting how badly a given signal will scatter. Astronomers use a quantity called the scattering measure, closely related to but distinct from the dispersion measure mentioned earlier, to characterize the cumulative turbulence. A higher scattering measure indicates a more turbulent, more disruptive path, translating directly into a narrower coherence bandwidth, a technical term describing the range of frequencies across which a signal's phase remains sufficiently stable for coherent detection and decoding. When a signal's coherence bandwidth becomes too narrow relative to the bandwidth needed to carry a given amount of information, the multipath scattering discussed earlier becomes severe enough that individual frequency components effectively decorrelate from one another, dramatically complicating any attempt to reconstruct the original signal. Astronomers have measured scattering effects directly for numerous pulsars scattered across the galaxy, building up a substantial observational catalog that reveals how scattering measure tends to increase with distance and with proximity to the busy, gas-rich galactic plane, while remaining comparatively lower along sightlines passing through the cleaner regions above and below that plane. This observational catalog provides exactly the kind of empirical grounding needed to move discussions of interstellar communication difficulty beyond pure theoretical speculation, offering real, measured numbers that researchers can use to estimate, with reasonable confidence, how severely a signal traveling toward or from a specific nearby star system might actually be affected, depending on that system particular location relative to the busier and calmer regions of the galactic disk. This same body of research has also revealed that Turbulence within the interstellar medium is not static, but evolves over time, driven by the ongoing influence of supernova explosions, stellar winds, and the slow, large-scale rotation of the galaxy itself, each of which continuously injects new energy and structure into the surrounding plasma. A nearby supernova, the explosive death of a massive star, can dramatically reshape the turbulent structure of the interstellar medium across a substantial surrounding volume for thousands of years afterward, meaning that the communication difficulty associated with any given sightline is not a fixed, permanent quantity, but something that can shift meaningfully over astronomically relevant timescales. A civilization located near a region that experiences a nearby supernova might find its communication environment substantially more turbulent for millennia following the event, compared to a civilization located in a comparatively undisturbed region of the galaxy, adding yet another layer of environmental variability to the already complex picture developed throughout this exploration. Understanding this connection between large-scale galactic structure, stellar activity, and small-scale signal scattering has become an increasingly interdisciplinary undertaking, drawing together researchers working in plasma physics, galactic astronomy, information theory, and space engineering, each contributing a different piece of the overall picture. This kind of interdisciplinary collaboration reflects a broader pattern common throughout the history of science, in which genuinely difficult, high-stakes questions tend to resist solution by any single narrow specialty, instead yielding gradually to the combined efforts of researchers approaching the same underlying problem from multiple complementary directions. The question of how to communicate reliably across interstellar distances, threading a signal successfully through a turbulent, storm-disturbed medium shaped by forces operating on scales ranging from individual charged particles to entire galactic structures, stands as a particularly vivid example of exactly this kind of deeply interdisciplinary scientific challenge. Bringing all of this together, the picture that emerges is one of a universe that is far more physically active, far more textured, and far more genuinely challenging to communicate across than the simple, empty vacuum imagined by earlier generations of researchers first contemplating the search for extraterrestrial intelligence. The interstellar medium is a living, turbulent environment, shaped continuously by the stars embedded within it, disturbed by their flares and coronal mass ejections, structured by supernova remnants and galactic rotation, and mathematically describable using the same fundamental turbulence physics that governs everyday fluid flow here on Earth. Any message attempting to cross this environment, whether sent by us or by some distant, unknown civilization, must contend with dispersion, scintillation, and multipath scattering, effects that no amount of raw transmission power alone can simply overpower. What scientists still do not fully know remains substantial, and it is important not to overstate the current state of understanding. The precise, detailed, turbulent structure along the vast majority of specific sightlines toward candidate star systems remains poorly characterized, limited by the practical constraints of what has actually been observed and measured to date. No genuine experimental test of deliberate signal transmission and reception across true interstellar distances has ever been attempted, leaving much of the current theoretical framework validated only indirectly through natural analogs like pulsars and fast radio bursts rather than through direct experimental confirmation. And the engineering solutions a genuinely advanced, technologically mature civilization might have already developed remain, by definition, beyond the current boundaries of human, scientific, and technological understanding. Current research continues to push against these boundaries of uncertainty from multiple directions simultaneously. Next-generation radio telescope arrays promise dramatically improved sensitivity and dramatically improved ability to characterize interstellar turbulence with greater precision than ever before. Continued study of fast radio bursts and pulsars steadily refines the empirical foundation underlying scientists' theoretical models. Serious engineering studies into concepts like the Solar Gravitational Lens mission continue advancing, however gradually, toward eventual technical feasibility and a growing emphasis on long-term signal integration, patient data archiving, and generational institutional continuity increasingly shapes how the broader search for extraterrestrial intelligence community thinks about designing search strategies capable of succeeding not within a single research grant cycle, but across the many decades this problem's underlying physics genuinely seems to demand. This topic remains scientifically important for reasons extending well beyond the specific question of whether humanity ever successfully communicates with another civilization. The physics underlying interstellar signal scattering directly informs humanity's own practical deep space exploration efforts, already actively shaping how engineers design communication systems for missions exploring our own solar system, and now, with Voyager, the very threshold of interstellar space itself. The same turbulence physics illuminates broader astrophysical questions about the structure and evolution of our galaxy, connecting seemingly distant fields of study, from space weather forecasting to fundamental plasma physics to the study of ancient, distant fast radio bursts originating from galaxies billions of light-years away, and the philosophical and institutional questions this challenge raises about patience, about generational continuity, about finding meaning in contributing to a project whose resolution may arrive long after any individual researcher's career has ended. Speak to something genuinely valuable about how humanity approaches its most ambitious, most long-term scientific undertakings. Perhaps what this exploration ultimately reveals is not a discouraging picture of an impossible task, but a clarifying one, a more honest and more scientifically grounded understanding of exactly what genuine interstellar communication would require. The silence recorded across more than 60 years of listening does not necessarily mean no one is out there, and it does not necessarily mean our own signals are failing to reach anyone. It may simply mean that the conversation, if it is happening at all, is unfolding far more slowly, far more patiently, and far more quietly than anyone imagined when the search first began, whispered across light years through a turbulent, storm-scattered medium that neither we nor any distant civilization can fully control, only patiently, carefully, and persistently work to understand. There is one more thread worth following before closing, because it connects the smallest scales discussed throughout this exploration back to the largest ones, the individual charged particles responsible for scattering a signal. the electrons and ions drifting through interstellar space are themselves the leftover material from earlier generations of stars, forged in stellar cores and scattered outward by supernova explosions long before our own sun ever formed. In a very real sense, the very medium that makes interstellar communication so difficult is built from the ashes of the stars that came before. A reminder that the galaxy's turbulent, storm-scattered nature is not an obstacle imposed from outside the story of stellar evolution, but an intrinsic, inseparable part of it. Any civilization attempting to speak across these distances is, in a very literal sense, trying to send a message through the recycled remains of countless earlier stars, threading a voice through the accumulated debris of billions of years of galactic history. That, perhaps, is the most fitting way to understand why this particular kind of patience, the willingness to wait, to encode redundantly, to time a transmission carefully, and to listen long after any single lifetime has ended, feels less like a limitation imposed on any civilization brave enough to attempt it, and more like an honest acknowledgement of just how vast, how layered, and how genuinely ancient the space between any two stars actually is. So, the next time you look up at a clear night sky, consider that the darkness between those points of light is not empty space, waiting patiently for a clean signal to pass through unchanged. It is an active, breathing environment, shaped by the very stars it separates, and any voice attempting to cross it must learn to speak the slow, redundant, patient language that turbulence itself demands.